Hello, and welcome to the Sleep Science Podcast. I'm Penny Lewis, a neuroscientist specializing in sleep and memory, and the presenter of this show. In the podcast, we talk about all things related to sleep, from dreaming and sleepwalking to what sleep does for our brain and body, and how we can get more out of our sleep. Please see the Sleep Science webpage for details. Today's guest is Tristan Bekinschtein. Tristan runs the Cambridge Consciousness and Cognition Lab and is not just interested in sleep, but also in consciousness, and especially the boundary between being conscious and unconscious. He's done a lot of exciting work examining this boundary and finding neural markers that indicate when we change between these two states. We also talk about left neglect, the bizarre phenomenon in which as patients fall asleep, they tend to neglect the left side of their world and why this might be. Finally, we talk about Tristan's work on resilience and what makes our mind resilient to stressors such as poverty. I hope you'll enjoy our conversation. Welcome to the Sleep Science Podcast. Thank you so much for agreeing to do this, Tristan. So my first question, Tristan, is it fair to say that your primary interest is actually in that intersection between wake and sleep or conscious and unconscious? And if so, can you tell a bit about how you got interested and why?
So I was working on people who are unconscious or have minimal consciousness because they have been involved in an accident or they have a sustained really bad brain injury that people usually call vegetative state, or minimally conscious people who are emerging from vegetative state, where you have this sort of weird state after a really, really bad, for example, car accident, where, the people definitely look awake, they open their eyes, but they don't seem to be able to react to the doctor's sort of interaction commands. So you ask them to move their hands, they don't move their hands. So you think, well, this patient is awake but not aware. So then you have your first definition, right, of consciousness. A person who's awake but not aware of himself or herself or their surroundings. So that's not a difference between being conscious or unconscious in the way we are conscious or unconscious of something. That's literally a dissociation between awareness and wakefulness. Yes, wakefulness, I'm awake. Awareness, there is no awareness in these patients. At least that's what the medics thought was the case. In some cases, these patients might look like unconscious from the point of view of being able to respond and think like we think consciously, but they might be in fact just trapped in their minds. And it could be that they can actually process what we say, but they can't act. They have a motor problem or an action in the brain problem. In those cases, people are not really a vegetative state. They are some sort of minimally conscious or some sort of other definition that we might say it's locked-in syndrome. Now, I spent years working with these patients, and it was extremely interesting and also extremely frustrating. And here it comes why I work on transitions of consciousness now, because it was so frustrating to work with these patients. Because the more I work with these patients, the more I help them in capturing different types of brain activities that may signal some degree of awareness in these patients, but I wasn't learning anything about consciousness itself. I was learning about the brain or markers in these patients are useful, but not what are the general ones between, in normal people, which is the majority of people. So I said, it's very nice to have a stable state of being completely unconscious, like a vegetative state, or completely conscious, like a normal volunteer who didn't sustain a brain injury. Everything in between, it's something in between. And that something in between, we call it a transition. When a patient is vegetative but is recovering, it's transitioning into recovery of being conscious. When you are asleep and you're waking up, you're transitioning from being asleep to being awake. That's a transition. At which point do you become aware of the world? When you're waking up. That's the limit we are interested in, right? We want to know what's going on between two allegedly stable states, sleep and awake. Or the other way, when you're awake and you're falling asleep, suddenly you become unconscious by sleep definition. That change that people say, I'm awake, oh, suddenly I'm asleep. It's not like that. It's more like a real mixed, semi-dynamic state. Things, get really misty, really complicated. I always call it the mist of consciousness. You can't quite see what's going on. If you're awake, the things are clear. If you're, asleep, the things are dark. If you have a dimming light, you can sort of play the game between, full light versus full darkness. How do you play that dial? in consciousness for people between awake and sleep. That's what I'm interested in.
So what you're saying is two things you've said, really. The first thing is that you were first working on patients who had loss of consciousness, due to some kind of damage. And that is the thing that led you to become interested in the transitions between sleep and wake, because you wanted to look at these transitions in healthy people as well as just in patients. So you could gain some more general knowledge that would be applicable to healthy participants as well. That was the first point. And then the second point was that you're saying it's not really like a black and white switch. There's more of a continuum. You are easing from one state to the other. You're not just flicking from one state instantly to the other. And it's kind of that gradual transition that you're interested in studying.
Yeah. I mean, I don't think there's anyone who truly does a switch between awake and sleep, except if you're narcoleptic and you, boom, suddenly become completely asleep. So you actually have to have a particular pathology to be able to have a real switch. Otherwise, none of us has a real switch, like a switch of the light. Everyone else has a dimming light. And some of us, we're the ones, you play the game with that dimming light. And when you're falling asleep, you're trying to think, am I drowsy? Am I asleep? Am I not asleep? So that sort of phenomenology experience thing of the transition is also something interesting. It's not just brain activity and behavior that we are interested in the transition. It's also what actually is happening in your mind as you do the transition. So it's a really complicated few minutes of your night, but it's really very interesting from the point of view of who we are. Do we become someone else when we fall asleep? Do we have a different life? Can we use that transition? Can we ease on, a different state? There's so many cool questions about this.
There's so many cool questions. So my first hopefully cool question is, to what extent do you think they're really parallel? I mean, the loss of consciousness in someone falling asleep and the loss of consciousness in a patient with brain damage. In both cases, they're losing consciousness, but it's not the same process. So can you really equate them?
I think you can equate in the same way you equate flying. Biologically, you can say birds fly and flies fly. So the evolution that gave wings to the flies happened millions of years before the evolutionary pressure for the birds to have wings. Those two serve the same purpose, to be suspended in the air and navigate in the air, aka flying. Now, the process that you reach those wings has absolutely nothing to do in terms of how happened evolutionarily, how it's constructed, the type of flying, the way the flies move the wings and the way the birds move the wings. It's very, very, very different. So, yes, between being unconscious or conscious in patients who sustain a brain injury and they're recovering, or between being unconscious and conscious of coming awake from a night, functionally, yes, it's a transition between two stable states. But really how it happens is extremely different, even if both happen in the brain. Now, you can push me a little bit and say, well, if you are recovering from vegetative state, at one point you are already been awake and sleep, because that's what happens with the patients. So it is an interaction between the two transitions and blah, blah, blah. Yes, it's true. But the brain complicated networks sustaining this type of transition are extremely different. One, it's within minutes, sleep and becoming awake, within seconds or minutes, depending on the type of wake. Unfortunate, wake you may have. If someone scares you and you're sleeping, that would be a couple of seconds. But if you're waking up slowly, then it could be minutes or hours. While the recovery from the patients, it's so slow because it entails new connections, recovery of neurons, whole pieces of the brain. So months and months of recovery. So it's extremely simple idea that to be able to drive your car is there in the garage, you start the car and then you go. So you go from idle to moving in a few seconds, waking up. If your car is broken, it's going to take hours to the mechanic to help you. It will go from idle to working by doing way more. So yes, it's the same brain, it's the same car, but in one case it's broken and needs fixing, and it takes time and a very different type of game than something that your system is prepared to do, basically waking up or starting the car.
Yeah, fair enough. So what you're saying is there's a parallel between the consciousness states, but the thing that has actually caused the loss of consciousness is quite different. And so the transition is going to be a different process, but there should be some kind of shared physiological basis for when they're actually conscious in both states. And maybe you can see that is missing in both of the unconscious states.
Yeah, so I fully agree. I mean, the being awake and aware after recovery from a patient, it's closer to a normal volunteer who's awake and aware. But if you think about unconsciousness, if someone is asleep, has a very interesting sort of brain pattern and, sometimes inner sort of life, like if they're dreaming, etc. When you're unconscious by the patients, your brain doesn't have an inner working that is easy to take out. In fact, the system is broken, so it's functioning in a very different manner. So one thing that is interesting with the patients where they're really months away of recovery, if they are in a path of recovery, is that the stable state of unconsciousness is extremely different from being asleep or being sedated. But when I say extremely different, it's brutally different. Of course, you can find mathematical measures of the brain activity that they look similar. They're completely deceiving. It's the same way that you're looking through very sort of foggy goggles and then you see something flying in front of your eyes and you say, was that a fly or a bird? Something flying through my eyesight. Yes, it was. You have no clue what it was. You just know it was flying. There are measures that the people use in the brain to define unconsciousness that they give you the same number for unconsciousness for patients in vegetative state, for sedation and for sleep. And that is what I call oversimplification.
So I know that you have a recent paper where you discuss this and you successfully developed some more sensitive measures using, I think, the P300 and looking at the early and late P300 and relating it to top-down and bottom-up processes in those three states. Can you explain a bit about that one?
So, the P300, this sort of weird name for a brain activity that we can see in the electroencephalography, and we measure brain activity through the skull. And if I show you something in the screen when you're using the EEG or I play a sound and you're paying attention, I might see at 300 milliseconds, so a third of a second after I present you, something in the screen or a sound, I see a little bump in the brain activity that we call the P300. So the positive signal at 300 milliseconds. Now, this only happens if you're really paying attention. So if you're paying attention and I present something, I will see your P300. That's great. Is that a marker of consciousness? It may be because, one assumes that to be conscious of something, one has to pay attention, or at least to a certain degree, it should be the case. So if I present these things to someone who's sedated, but we think they might still be aware, then I present a series of sounds and I say, pay attention to these when you hear the sound. I give them sedation and they start to look like they're sedated, maybe not unconscious, but, pretty down. I might or might not see those P300. It could be that sometimes they are actually unconscious and then I don't see those P3 because they couldn't direct attention because they were sedated.
So you only get the P300 when they actually, not only that they hear the sound, but they process it because they direct attention to it.
I think that they actually process it all the time, but they don't pay attention to it because they can't. And hence you don't see the P300 because you see the other brain activity before the P300 that they are processing the sound in the brain. But because they can't pay attention because they are unconscious, then you don't see the P300. So it's the loss of the P300 that tells me that, yes, there was a processing in the brain, but no, I don't see a P300. So most likely the person was not able to direct attention to the sound I told them before. Now, if you're a patient, vegetative state patient, I tell you, I know you can't really hear me, but maybe if you're one of those 10% of patients that have been misdiagnosed, you hear the sound like this, just count that sound. I know maybe you can hear me, count that sound in your head. I'm going to play this series of sounds for 3 minutes. You play that and you do the analysis and you see P300. You don't have other way to conclude that this person first understood the instruction, pay attention to this. And then you saw the P300. You of course, in the same patient, you can play the sounds without giving the instruction and show that if they don't pay attention, they don't have the P300. But if you see it, it's difficult to say, oh, this person is unconscious, right? Because you see a marker of attention. So if they can understand and apply a rule of count these sounds, I would say they're conscious. For those P300 to happen, they have to be sustained, nice, well-rounded P300, not just little blips that look like attention, but they are not. They have to be sustained, what we call late P300. So they start and they are there for hundreds of milliseconds. That in brain activity for neuroscientists is a lot, right? I mean, a lot of time in brain time. So it's a nice signal to say, hey, attention was there.
So it's a big, strong signal that you can see. And so you can say, you can speculate that this person is not really in a vegetative state, but they're just in a minimally conscious state. And so they did understand and they could pay attention. Yeah, that's really exciting, actually.
Yeah, but the cool thing is that the P300 also disappears when you give them more and more sedation. So we do have the P300 as a marker of consciousness that it's not very specific, right? If you're a patient and you're recovering and I see your P300, even if it's a bit distorted and weird because your brain has holes and all of the bad things that happen when you have a really bad accident, I know it's a P300 and it only happened when I ask you to pay attention and it looks like you pay attention because I see your P300. If I ask you, Penny, to come to the lab and I give you the sedation and it slowly goes down and I see your P300 and suddenly I don't see your P300 anymore, I know you're not paying attention. I see still the weird brain forms and brain markers that you are hearing the sounds that I ask you to hear, but you're not showing me the P300. So I actually seen the loss of the P300. So now I have a marker of consciousness when you're conscious and a marker of unconsciousness when you didn't pay attention. So in this case, the P300 is one of those signals that is not specific about the type of unconsciousness. It's only specific of the type of attentive consciousness.
So fine. So if I'm sedated, I won't be able to pay attention and I won't exhibit a P300. But what about if I fall asleep? Is it the same?
So no, it's not the same, but it's not that different. So the interesting thing, because the P300 is so inspecific about unconsciousness, the P300 starts to be distorted as you fall asleep. And when you are truly in light sleep, but truly sleep, what we usually call N2, the P300 is not really there. But it might come back, and this is, there's only a couple of papers that it might come back in REM when you allegedly are conscious, but trapping your sleep. Or the other type of consciousness, the dreaming consciousness.
Yeah, we have seen it in REM in my lab, actually. And in the same participant, in the same night, we see it in REM and not in non-REM. So it exactly fits the pattern that you are describing.
Yeah.
Yeah, it's a great marker. It's really interesting work on the vegetative state patients. So let me ask you now about another kind of work that I know you've been doing on losing consciousness. You have a paper about how people neglect the left side of the world as they are falling asleep. It's a quite different phenomenon, but also very interesting.
Yeah, so the cool thing about that paper was it was coming from the clinical literature. So there are these sort of weird neurological syndrome that someone has lesion in the brain, usually in the frontal or parietal, so the front of the back of the brain, that makes their left side of the world disappear. It's really weird, right? I mean, because they have this brain lesion and suddenly in the left side of the world, they don't see that. Or at least they say they don't see that. They don't seem to be aware of that side. In the extreme version of this, the men would shave only the right side of the face and would not shave the left side because they don't see there is hair there. In fact, it's even weirder than that. They don't think that part of the world is a part of the world. So there's different levels. So you can have such a severe neglect of the left side of the world that you might say that ontologically the left side of the world doesn't exist. That's just crazy, right? I mean, we know the world exists even if we don't see it. So if you have this, spatial neglect as a patient and you don't see the left side, then it's not that bad. It's not that you don't think it doesn't exist, but it's just not, you don't see it. Now, when they did this experiment in patients, showing them things on the left side, the patients, the things happening on the left side, but they said they were not there. So they couldn't detect them, for example. That's a great definition between what is process, as we were saying before, and what is awareness. So they were not aware of the left side of their world, but it was processed in the visual system, right?
So they're not paying attention to it. That's what you're going to say.
Well, maybe they're not paying attention, or maybe they are paying attention, but they are not aware. So here we go in the subtlety between attention and awareness. And it might be one of those weird cases. We tell them to pay attention, but they still don't become aware of it. So if you really play the game with some of these patients, the stable ones, you can direct their attention by flashing something really big on the left side. Do you see their eyes moving? And then you show something else and you say, did you see the red dot or a green dot? And they will be above chance, but they won't be perfect. If I ask you to do this, you will be 100% correct. I mean, green or red, unless you're a chromatic, you will say green or red. These patients, even if you direct their attention there, they might still not be aware of which was the color. So it's a bit weird, the definition between attention and awareness. But the interesting, weird thing about this is that we can reproduce this in other type of problems. So in the clinical literature, there were some old papers in the 90s saying that people start to make more mistakes on the left side of the sheet of paper than on the right side of the sheet of paper when they were a bit tired. So you have people who have some mild brain injury and they become less attentive because they have the brain injury. They can't concentrate very well. So they ask them to cross a whole paper A4 in horizontal full of dolphins and other animals. And you have to cross the dolphin. And they, as they were a bit tired of doing this boring test, they started to cross less than normal dolphins on the left side of the paper than on the right side of the paper.
But these are healthy people, or these are people?
These were people who had some brain injury, but after an accident, but they were chatting with you and they were okay. They were recovering, right? But, there was some degree of neglect, not like the brain lesion patient that they don't see at all on the left side. But there was a bit of a, imbalance between left and right of their world, which was rather interesting. So with Corinne Berham, we started to discuss whether we could do that if the normal people were a bit drowsy. So if you make the people, come to the lab and listen to sounds coming from the left or the right, will they make mistakes or not detect the sounds on the left compared to the sounds on the right? It's a wild assumption, assuming that normal people can be like patients with brain injury. And we did a couple of pilots, like 3 people, and all of the 3 people immediately, and it just came like brutal. When the people were drowsy and we could see they were like getting really slow in the brain activity, we could see they were falling asleep. They started to literally forget the sounds were coming from the left and pressing the button to the right. So they were saying that half of the sounds coming from the left were coming from the right. Half. That's ridiculous.
It's amazing.
We literally blowing horns on the left ear versus the right ear. So there was no mistakes when you were awake. When you were drowsy, it's just brutal. And we thought, well, just lack 3 people. So we did 9 people with a different paradigm, now with a guitar. And we make Tom Manley, another researcher that we were collaborating with him, to basically, record the guitar physically. So we put the microphone in stereo in a recording studio. And we make him move, from the center of the microphones to the left 10 degrees, 20 degrees, 40 degrees, 60 degrees, and to the right the same, to record the most perfect stereophonic sort of naturalistic guitar sound. We did it with another 10, and it came out brutal effect, impressive. Not just simple sound left or right, but just real life small degrees of change of someone in front of you with a guitar. And then we did the experiment and it came out really strong. And then someone else did it again in Germany and again in Mexico, I think. So it was one of those experiments that is easy to replicate once you understand what to do. And it's true. And people weirdly neglect the left side, not like patients, but they make mistakes from the left and not from the right when they're drowsy.
So it's crazy, right? I mean, it's really bizarre. Why do you think this is happening? What's going on?
So the interesting thing is that, one can sort of construe this thing in terms of attention, right? Spatial attention, attention to the left, attention to the right. Do we lose the capacity to hear sounds from the left side of the world, or do we lose the capacity to attend those? Or do we lose the capacity to become aware of those? So the people were aware of those, but they were making mistakes. So people didn't stop responding to the left side sounds. They made mistakes. So they thought, they misconstrued that they were coming from the left, and they misconstrued they were coming from the right. So they said, oh, yeah, that sound came from the right, but actually was coming from the left. So it's a problem of attention, because in terms of sound, they were always detecting the sound, even if they were drowsy. So it was really a little problem of discriminating where it was coming from. But you know what? They didn't say they were less unsure necessarily. So we did a little, metacognition. We asked them, how sure you are. And for the difficult sounds, the ones that are like 10 or 20 degrees away from the midline of your nose, those were categorized as difficult, left or right. But they were making more mistakes when they're coming from the left, when they were drowsy, than from the right. So it's not a problem of you being confident. They were equally confident. They were just misconstruing the attentional space of the world. So we know it's attention, and which is really good. Or if you think about it, we know it's a problem of information about the space. So decision making. So the information about taking a decision. The sound is processed correctly. The button press is done correctly, but the discrimination of the information, it's just warped. So there's something happening in the brain.
So it's something about, it's processed, but it's something about the way it's processed and the way meaning is assigned to that incoming signal that is distorted or it has more noise. Maybe it's just a matter of additional noise in that process, since they don't get them all wrong, right?
Yeah, no, not all wrong. No. But the interesting thing is that it's noisier on only one side of the world. So one of the hypotheses that we think is sort of pretty cool is the idea that the way we have brain wire to process the left and the right side of the world is different. Whatever happened in evolution, or whatever happens, the fact that most people is right-handed, or most of the time people have language primarily on the left side of the brain, or at least primarily on the left side of the brain, there is something about spatial attention that also it's not equivalent, between left and right of the world. So if that's the case, then when you're getting drowsy, if you think that drowsiness or the process of falling asleep is impacting the whole brain, and these two parts of the brain, the one that is more related to the left and the other one related to the right, are different, they will be impacted in a different manner. So this lower gain of wakefulness by falling asleep is impacting the attentional processing of left and right in a differential manner, differently. And we think that maybe that is what is happening, because it's not auditory and it's not motor. It's literally an attentional evidence, the evidence of what is coming from the left or the right.
It's so bizarre. It's really interesting. I'm wondering if it links into another story that you published recently, also on this falling asleep topic. So you have this paper about reconfiguration of underlying neural processes and networks as people fall asleep. And it feels to me like turning down the dial on the attention, how it differs between right and left, might relate to a reconfiguration of networks. Is that what you think, or can you comment?
Yeah. So initially our experiments a few years back were trying to capture the behavioral difference, right? So people were paying attention to the left or to the right and then pressing the button, and we saw behaviorally they were making more mistakes to the left or the right. When the people were getting drowsy, they were taking more time to take decision on one type of information than another type of information. So we started to slowly map in a series of 7 or 8 experiments that drowsiness affects several cognitive aspects of simple decision making. Sometimes semantic aspects of things about words and processing, sometimes syntactic, sometimes spatial attention, that the one we were just chatting, sometimes about our capacity to process information that it's maybe ambiguous. So the one that you're referring to is a good example, because so we hear words that were left on the left ear and right on the right ear. If I ask you to press the button, you're really fast. But if it says left on the right ear, you're still going to press left in your hand, but you're slightly slower. We appear on the right side on the right ear. So that thing that we call cognitive control, don't press to where the sound came from, press to what the sound was, which is the word left or the word right. So that inhibition that people talk about it, that thing is something that it seems to be maintained when you're drowsy. So you still can do it, either the one that is right on the right or the one is right on the left. You still do it correctly, but you're slower in both cases.
So let's just make sure it's clear for anyone that's listening. And this is something that in psychology, I think we would call a Stroop effect, where you've got information that is conflicting. So for instance, in this case, you hear the word right and it's coming from the left side, but that means you have to press the right button. Or you could do it as well with colors. It could be something is red, but it says green in red, and you have to therefore press the green button, even though it was red. So it's where you have to deal with some kind of a conflict like that. That is quite a tricky cognitive task. And so what Tristan is saying is people can still do this as they get drowsy. They just get slower.
Yeah. And the cool thing about the Stroop-like effect is that it's one of those effects that, you are either slower, you make more mistakes if you have to inhibit one piece of information to give primacy to another one. It's such a strong effect that you can get it in every person. So here you go, where Tristan likes to dwell in, as a biologist, dwell in psychology. I don't deal with small effects. I don't like small effects in psychology. I want things that I can see in every person. I know it happens. and then I make them fall asleep. And then I test whether awake or drowsy or different type of drowsiness modulate that strong psychological effect. So that's an important aspect of my lab, that we don't really want to work on small, inconsistent effects. Some people see the effect and you don't see the effect, etc. We want to work on projects that the effect is very strong in awake, and then we see what happens in drowsy or even in sleep. And that's why this conflict left-right side meaning effect was nice, because people don't make mistakes. People just are slower. So there's a beauty there of people still process correctly. They're just slower when the information is incongruent.
But you did find an effect in what's happening inside the brain, in the brain activity, right?
Yeah. So that's the cool thing that we were talking about. Drowsiness must be doing something to the brain network processing information that makes it work different. When you don't find an effect behaviorally, an effect between the two different conditions, the easy left on the left and the difficult left on the right, there's a main effect of being slower in drowsy, but there were no differences between these two effects. But the brain activity was brutally different. And that's really cool, right? Because that means that the brain is solving the problem, but possibly in a different manner. And we have another paper we're going to submit soon, where we make them maybe being awake and falling asleep, and we see that they still have the effect that behaviorally, so they still press the button slower to the left on the right ear or the right in the left ear, and we still see the brain activity changing to solve this problem. So very different brain activity to solve the problem of left on the other ear between awake and drowsy. And then we take the same people and we sleep deprive them. We really mess them up. So now they come back to the lab the following week, completely sleep deprived. Like they slept 2-3 hours. They really hate us. They come to the lab and then we tell them, do this awake, hold it there, don't fall asleep. And they are really annoyed, but they still do it and they don't make mistakes. And they're a bit more noisy, as we say, but they still have the effect, the famous conflict effect that we were talking about. And when they are drowsy and sleep deprived, they still do it, but really bad, but they still do it. So we're still there. And the brain activity changes completely, even more. So they're still solving it, but it's as if they are really pushing the brain systems to the limit by sleep deprived and drowsy, and you're still doing it. So we're really pushing you as much as possible.
So what is this change in brain activity that you're seeing?
So we have an impression that it's as if you were calling friends in the brain to help you. Because what we see is like an expansion of the brain networks needed to solve the problem. So as if you're using more resources to solve the same thing. I mean, we all been in that moment if you're a caffeine addict like me. And you wake up slightly earlier because you have to take a train. You wake up earlier and you still want to make yourself a coffee. And you're so bloody slow and make mistakes. But you're still doing it, right? But it takes so much effort. And I can assure you, using much more resources from your brain to make a coffee. Because you're effectively, deprived from your normal resources by the sleep deprivation and drowsiness that you have before getting your caffeine shot. I think that's what we did with the poor people. Sleep deprived and drowsy. Still doing it. And calling all the friends in the brain, all the possible resources to solve the simplest, boring task of left on the right side of the ear.
So basically the network in the brain that's used to solve the task is expanding. You're using more areas. And is that something to do with attention? Do you think it relates to the left neglect problem that we talked about?
The interesting thing is I don't think it does. So we did look at left and right differences in this task, because you have left on the left ear, right on the right ear, but you have left on the right ear and right on the left ear as words. So you can actually look at whether there are differences in the processing of the left, right, correct and incorrect match. And there were not clear differences. So it didn't look like you were, because again, it wasn't important for you to pay attention to the space. Your task is to try to avoid paying attention to the space and pay attention to the meaning of the word. So very quickly, you try to avoid caring about the space. If it's coming from the left or the right ear, if it says left, I should press left. So you're making the biggest effort possible to literally avoid spatial attention and only care about the meaning of the word. And then, even if you're really drowsy, we don't see the difference between left and right. We see the difference in the brain networks.
Did you do that on purpose? Try to tap different systems, or did that just kind of fall out of the experimental design?
No, we were discussing quite a lot, because we have a companion paper with some collaborators where we do up and down. not only left-right. So we do this conflict effect between top and bottom, and another type of conflict effects, playing the game between spatial attention in left-right versus top-bottom, and etc. And the cool thing is that, it just is all very systematic. So we knew we were going to do the left-right on purpose. And if we had the spatial effect, then we could combine effect. But if we didn't, because we were neglecting it, then we would be able to say the effect has to be related to what you're doing. Because I think it really depends what you're doing, how drowsiness affects you. It's not a general blanket of lower cognition that you gain from drowsiness. The transition affects, in a differential manner, different things that you can do, different cognitive processes that you can do as humans and probably as animals.
Yeah, so different systems in the brain are influenced in a different way by this kind of drowsiness. And if we go back to this concept of the transition, the gradual transition we were talking about, you said you're kind of turning down the dial, and as you turn it down, you're influencing maybe one system after another. It's so fascinating. I want to ask you about a different aspect of your work that builds on this or relates to this. So I know that you have some exciting work about which kind of things can be processed then when you are fully asleep. And I guess that would be when the dial has been turned all the way down, or, as far down as it goes in light sleep. I know you have work, for instance, about semantic processing, showing that maybe you are listening to sounds, words that are played, and you can respond differently to those. And you have other work, so maybe you can just expand on it.
So there's one part of the work where we try to see the fragmentation of behavior as you fall asleep, right? You see the person is pressing the button correctly, doing the task, and then they get slower. Sometimes they make more mistakes. Sometimes they don't make mistakes. They just get slower, depending on the type of task. And sometimes they don't make mistakes. They become slower until they stop responding. And then you can say, oh, they stop responding. We can go in the EEG and see, is this like true sleep and true sleep, or we're still in the late part of the transition? So one aspect is that one can separate what we think is still a transition, but there is no response, versus the transition is over. Now we're in a stable state of sleep called N2 with particular brain markers, and we know this from the 50s, so that's all very nicely defined. Now, because the person was doing things while they were falling asleep, maybe there's some still workings in the brain, like holding into like a working memory into the sleep. That was one of the things. Why we thought that is because we know that whatever happens during the day is very likely to influence your dreams. Even more, there's a lot of accounts of people doing something during the day and having these sort of visions as they are falling asleep that are related to the day. So we knew you can carry over whatever you were doing during the day into your sleep. But we thought, well, maybe sleep destroys that you were doing up until you're back in REM, fully dreaming, and then maybe comes back from memory. And you know very well from your work that memory, reactivation and consolidation during sleep is very important. So of course, it's important what you present when you're awake to what you get during sleep. But the question is, can you maintain an action in the brain? That was the key thing. So very early on in 2009, I did an experiment, which is the simplest experiment. This sound to the left, this sound to the right. And you fall asleep, and when you're not responding, I know you're very likely to be asleep. And I go back and I look at the brain when you were asleep, and I try to see how does the brain respond to those sounds. And I look at the brain activity, and I see there's brain activity related to the auditory process, and it's all very nice. And then I ask myself, what if the motor activity, the preparation to press the button, is still there, even if the person is not responding? It was a very simple question. I knew I was interested in separating what is action from audition, from processing of the information. These three classic things of cognition. So I knew the person was not responding, and I knew the person was definitely processing auditorily. So what I could do then was to see if the brain activity that it was in preparation of pressing the left hand versus the right hand was there. That would tell me that the person was hearing, discriminating if had to press the button left or right, but would not be able to press because they were asleep. And that I saw it very early on in 2009. And then I took a train to go back to Paris, and I found by chance in the train a researcher from Paris that I knew from before very briefly. And he was sitting there with another researcher from the UK. And we sit there and I tell them, you know what? This week I found this weird thing. I think it's awesome. I'm going to follow up on that. And then Sid sort of jumped from the table. Wait, with his French accent. He's like, this is great. He's like, this is absolutely great. We have to do something with this. And he went into this rant about the whole world of awareness and consciousness was based on very faint stimuli. They present something and then they mask it. They make it very difficult to understand. And then they see if the person still processes in the brain, but they don't recognize it. So you separate, the processing from awareness. This whole thing of masking is it relies on degrading the information. You hear a word and then you hear the word with more noise and more noise. If I say a word, the word show, and I add noise, it says, and you only know that it says show because I told you before. If I say another word, for example, I said screen with noise. You can't possibly know it was a screen unless I load the noise. I said, and you say, oh, could be screen. The whole cognitive neuroscience of awareness is based on this weird degrading the stimuli to make it unconscious but still processing. And he said, this, what you told me, doesn't do that. You always present the stimuli perfectly well. For example, the word screen would be this word screen. But what is degrading is the brain, is wakefulness. Let's say, yes, man, that's great. Let's do a semantic experiment. So within a couple of weeks, he said, I have a student, send it to Cambridge and you can do the experiment. And we did the experiment very quickly. I showed her my results from the tones. We said, let's do it with the words. There were half of the words were animals, half of the words were objects. So a normal waking person will hear giraffe and press the left button and hear table and press the right button. So it would be like dead simple, like an idiotic experiment. And then would it be possible for us to, when the people are not responding because they're falling asleep, would it be possible for us to see if they were still categorizing the words? So we had a list for awake and a list for sleep. And when the list of awake finished and the person stopped responding, we started a new list, the list of sleep. And most of the participants didn't wake up. Some of them wake up and started to respond to the new list. And so we exclude them. So we did 60-something participants and we end up with 19 who were unresponsive the 6 minutes. During sleep, the 6 minutes, we presented a new list of words. And from those 19, we did the experiment and we saw that they were definitely categorizing the words in animals or objects. So the semantic separation. They knew the meaning of the word, even if it was the first time they were hearing it that day. But they prepared to press the left button, but they never press because they were asleep. But in the brain, we saw the activity to the left preparation, practically the same.
So you could tell they heard the words and they processed them in that they knew which button they should be pressing. They just couldn't actually press it.
Which is great. To a certain degree, what we're saying is there's things that are so ingrained that they will go through the transition. So we did a little experiment that is not even in the paper, where we presented the first list in awake. Then we let them fall asleep without presentation. Then we presented the second list. Absolutely nothing. If you don't do it during the falling asleep process, you don't carry over that rule of categorizing. You have to be actively doing during the transition for us to see that you're still doing it in your brain. So I think it's super important to understand that it will only work if you're doing it while falling asleep. The follow-up experiment by Thomas Brillion, I think it's even more interesting. So he took the one we did, with Sid and Luis, and he did it with the words versus non-words. Instead of the type of word, animals or objects, he said words versus non-words. Things that sound like words but are not. And repeated the experiment, and it came out the same way, so he went into the paper, and then he continued to do a follow-up experiments where they kept on doing more and more words into deep sleep and REM and etc. And the beautiful thing is that they lost the effect that you see in light sleep. You lose it in deep sleep. So there's a point in sleep that really wipes out your capacity to process that information.
That goes back to what you were talking about, the transition and kind of gradually turning down the dial, right? Yeah, that is really an interesting way of relating everything together, actually, isn't it?
Oh, yeah, no, I was super happy when Thomas decided that was a project to follow up, because at the time they said, we would like to continue that. And I said, carry on with this, because I'm now on these conflict effects and the spatial attention. And they continue to do that. And they went deeper into sleep, which I wasn't going to do. So it was great to see the other side of the next transition between light sleep and deep sleep, to see that the light sleep versus deep sleep also fragmented that processing that we saw maintained in light sleep.
I'm also very interested by the fact that you said they have to be doing the task during the transition as they're falling asleep in order for this to work, because that's quite a different kind of effect than if they had just learned the associations in wake and then you trigger, as you said, some kind of reactivation of the response in sleep. But, if they learn those associations between the animals and objects and which hand they should press, if they learn that in wake, and then hours later, they fell asleep. And in deep sleep, in light sleep in this case, you played those animals and object words. You might still expect them to have this motor activity, but it could be for a different reason. I think that's what you're saying. So it would be triggering a memory rather than that they're still kind of doing the task in a sense.
I think that the type of memory that you hold and maintain if you're doing it during the transition is an active, continuously active memory. It's not a reactivation of a memory because you're doing it until you stop doing it. But the fact that you're not doing it, that doesn't mean that your brain is not doing something because you keep on presenting the same information as you fall asleep. While in the case of you training in doing some task or association between left animals, right objects, and then stopping for hours, and then during light sleep, reactivating the memory doesn't necessarily reactivate an active rule of pressing left or right. It definitely reactivates something you did during the morning or the afternoon, but it doesn't reactivate the whole complete process action. It might be that playing the game in more training or a different type of decision, maybe it does reactivate the whole up to the action, but not action. We didn't find it. Again, it's not something we pursue in several experiments, but for us it was very interesting to see that we knew the effect was clear, and when we didn't present it during the transition, we couldn't see it. We could still see differences in the sense that we still knew that they were processing words and not sounds. So that was really cool.
Yeah, so they're still processing the information that's presented, but they're not linking it to the movement. They're not trying to do the task. I think that is an important distinction, and I think it's really interesting.
Yeah, and the right experiment to do there, it's to have two categories and then try to separate the categories. Don't do it during the transition, and then try to separate the categories when you present them in the brain. So you try to find the neural differences between animals and objects without caring whether it's motor related or semantically related. So you really want to see if you can still process the semantics even if you don't move the semantics up to the action of pressing the left or the right. I think there's this idea of the disconnection between the knowledge you have in between whether it's an animal or object should still be present, even if you don't link it to the action itself. So I think the ideal experiment is to have a list that you heard during wakefulness, play again, intermix with a list that is new, and see what happens there.
Yes, but if they're processing it, if they're really hearing and processing, they should also have the same responses to the new list, right?
I would hope that there will be a responses of them categorizing animals or objects, plus a signature that they reactivate in the memory they heard that day, versus the new list. They don't reactivate the memory necessarily because they didn't hear that word, but it's semantically related, so there's definitely help. Then you will still see the differentiation between animals or objects, but I don't think you will see, or maybe it won't be obvious, an activation of the areas of the brain that allows you to press the button, so the action related areas. Again, up for grabs, right? It's a cool experiment.
It's a cool experiment. I think it's technically tricky, but it's very cool. I wanted to ask you, I know that you are from Buenos Aires and you have some interesting collaborations with groups in Buenos Aires and also in Brazil, I believe, about resilience in vulnerable populations. Can you just briefly talk about that?
Yeah, so 5 years ago, after I was already full on the transitions, I started to develop the other research program that I'm doing now, which is slightly more related to the idea of challenging the system, the brain, the cognitive system, by different ways. So the idea that if you're still doing things where you're getting drowsy, that means that there is plasticity in the brain and compensatory mechanisms to still do stuff when even you're definitely getting, a challenge, which is falling asleep. Same thing when you're getting sedated, right? So the brain has plasticity and capacity. So that concept is the concept of resilience. So that led me into, a long discussion about resilience in natural settings. So people under stress. Could be poverty, which is a very strong stress for people and very common around the world. And poverty is a really, really strong stressor because it's a compound stressor, right? I mean, it affects practically everything in life. And in between people who are under poverty stress, if you want to simplify it in a way, some of them quite resilient, some of them are not. So what makes someone resilient in those terrible settings? So you don't have much electricity, you have to walk 300 meters to get water. So there is definitely not an ideal situation, but it's a fairly common situation. And then people are still doing well. Some people are still like happy and getting by, while others are basically catastrophically failing, doing something terrible psychiatrically or putting themselves in danger. What is that makes them resilient? And that is the question. And that's what we are working with. I mean, stressing brain and cognition by poverty is definitely not the same as stressing it by falling asleep. But I think there's parallelisms about the plasticity of the system.
I see. Yeah. And I think it's a really important topic as well. If you can understand what allows some people to deal with that stress very well, then that could be very useful, valuable information for other people to have.
Yeah, definitely. Although it's a bit of a double-edged sword if you think about it politically, right? In the sense that you don't want to apply a solution that it's on the person, because that's not a structural solution. The solution is to revamp the system so they are not poor. So it's a weird clash between us trying to understand what makes the people break and what make people sort of bend and still be there when they're under poverty stress, which is very, very important and useful for resilience. But the solution to poverty is not to train resilience. The solution to poverty is to reinvent the way the society treats its individuals. I'm a bit torn sometimes.
I see that, but I also see that it could be helpful to people who are in that situation.
No, yes, definitely.
So it's a great project. Okay, so let me just finish by asking you a couple of quick questions. So firstly, what do you see as the big, exciting next questions to ask in this field of transitions in consciousness?
So I think that the transition is a great model for two reasons. It's a theoretical model and experimental model. It's a theoretical model because it allows you to separate what is commonly used in science, stable states, versus what it's not so commonly used in science, which is the changes between those states. So people tend to say, oh, this situation was stable, so I could ask this question. And I say, no, you want the situation to be unstable. You want the situation to be dynamic, because that's how we go around life. That's how cognitive psychology, cognition works. Never choose stable. Is most of the time actually you switching between thoughts, between things you're doing, actions, etc. So it's very dynamic. So we need to do our science in a dynamical manner. It doesn't need to be uncontrolled, but it's an experiment that is closer to what we evolved to be, which is very flexible and ever changing. So I like the transitions as a very clear model of how cognition works, because it challenges cognition and it's continuously going up and down. Nobody falls asleep by being awake and slowly, like in a slide in the park, going to light sleep. Everybody goes up and down. Wake up, come out. I have never seen a person that it's beautifully gets slower, then makes a bit more mistakes, then gets even more slower, then misses a few trials, then misses more, and then they stop responding. So I think that's a theoretical model that forces you into going into the dynamic cognition. And the second one is that transitions allows you to be an experimental model for cognition in general. You can have your little pet hypothesis about your cognition. Could be anything you like, and you work on working memory. How does working memory changes with drowsiness, or how does working memory changes when it's stress? Do you have less precision in working memory, or do you remember less items? How does it work? How do we do that? Oh, we stress the system instead of stressing the stimuli. Oh, good idea. Shall we give drugs? No, make them drowsy. Oh no, make them sleep deprived. It's an experimental model to push forward cognition.
Okay, yeah, I see that it's a great model. And then just building on that, another quick question. There's a lot of stigma around the study of consciousness, just like there's stigma around dreams, studying things like that. So how do you feel about working in that field? Do you think that by having this model, which is about transitions, you kind of avoid some of the stigmatized areas? Would you encourage young people coming into cognitive neuroscience into this area, or what would you say?
I think the stigma of consciousness is gone in the new generations. And I'm glad for it because it's just another cognitive processing and has a lot of baggage philosophically, historically. But truth is that the new generations don't care. When I talk to students, they couldn't care less. They see it as another, topic to discuss, which I think that's basically how it has evolved through the years. In the 90s, first neuroscience of consciousness was taboo. It's been 30 years. I think we're fine now. I'm glad we're fine.
Yeah. Okay. So great answer. So you would definitely encourage people to go into this kind of area. So thank you so much, Tristan. I really learned a lot by listening to you and having this conversation. It was a real pleasure. You've been listening to the Sleep Science Podcast with me, Penny Lewis. My guest today was Dr. Tristan Bekinschtein from Cambridge University, and our producer was Sophie Smith. If you've enjoyed this show, please consider subscribing to the podcast or liking us on Twitter. We're planning a Q&A session for the last episode of this series, so if you have questions about this episode or anything to do with sleep, please send them to our Twitter account @Sleep Science Podcast Q&A. If you'd like to hear some other podcasts on sleep, please check out The Blunt Report, which has recently released a whole series on this topic, including a really nice episode on the curious case of fatal familial insomnia. The Blunt Report in general aims to create interest in the world around us in a relaxed way that's easy to follow. Host Connor Blunt has spoken to some fascinating people, and it's well worth a listen. The Blunt Report podcast is available on all platforms and even has video podcasts on YouTube. Thanks for listening today, and until next time, sleep well.